Swayam Prabha. Digital India. Educated India.
Welcome to module 7. In module 6, we looked into the strength properties or strength related properties of concrete, and in this module, module 7, we shall be looking into creep and shrinkage of concrete, two other important properties, or rather behavior of concrete. And in the first lecture, we will start with creep, and outline of this lecture is first we will talk about or rather we will introduce creep. There is something called relaxation, we will also talk about that, mechanism of creep as much as possible, effect of various factors, aggregate, modulus of elasticity, temperature, etc., and lastly we will look into part of the prediction, which would continue to the next lecture as well. So, let us see what is creep. Now, in material science, creep is the tendency of the solid or of any solid material to move slowly or deform permanently under the influence of stresses. So, basically it has a many materials have tendency to move slowly or deform permanently under influence of stress. Now, metal exhibits this under certain conditions, polymers also exhibit this, and of course, concrete does. Therefore, what it means is that it occurs due to long term exposure to stress, and obviously, they will be below the strength, because it will not fail. So, below that there will be deformation long term if you expose them to long term stress. That means, stress you have and you keep it, maintain the stress, it would show deformation, move slowly or deform permanently. So, therefore, that is what is creep. Creep occurs in metals, polymers and concrete. Creep of concrete is different than of course, others, creep of concrete, creep of concrete, creep of concrete is different than others. Mechanisms are different, because the materials themselves are quite different. So, let us see, supposing I have a concrete and I apply stress at some time t 0 as shown here. This axis is stress, this axis is age, and put it to some value of sigma 0, the stress level, and maintain the stress constant. Therefore, sustained loading, kind of sustained stress, right. So, expose it continuously, continuous exposure to a stress. Let us see what happens. Sustained stress as we have applied, then at the same time t 0, the strain would be elastic strain, because instantaneously there will be elastic strain due to this. So, there will be some elastic strain, because I have applied the stress. So, initial elastic strain will be given by this sigma 0 divided by modulus of elasticity of the material. And as the time progresses, you find there is some sort of deformation occurring, and if you consider the time t, when I have sustained the loading, as we have seen, we have sustained the loading t and beyond. So, at point t you find some additional deformation under this constant or additional strain under the constant sigma 0 is been observed. Sigma 0 you have not changed, but with time you find there are additional deformation, additional strain, and therefore, the creep at this point will be defined as strain at E t, which is the sum total of this at t, it is sum total of E 0 plus the creep. So, therefore, E is E t minus E 0, that is what is creep strain after time t minus t 0. So, that is what is creep. Concrete exhibits this behavior, many other material does, but concrete does, that is what is of our interest at the moment. So, that is what it is. So, this resulted in strain, sustained stress, resulted strain. We find that there are two componented instantaneous elastic strain, and with time there will be some more strain, which is of course asymptotic to some line, and the difference between these two we call as creep strain or creep simply. If you look at the stress strain diagram, right, epsilon t, stress is sigma 0, same stress is sigma 0. So, instantaneous at E 0 is this much. So, this is my initial elastic strain, stress strain. So, this is the stress, this is the strain. As I increase my stress, it reaches to this strain, and let me keep it there, do not increase it further as is shown here, but the what will happen after 7 days of loading, you will find there is some increase, and further increase at any time you will find the strain is increased further at E t. So, therefore, creep is E t minus E 0. So, this is E t minus E 0, that is the creep. So, say some days and 7 days under load, 28 days under load, 100 days under load. So, at any time after t minus t 0 under load, stress strain behavior will change. In other words, effective modulus has also changed, So, if I am considering at some later time, I find that the actually for example, if this is my stress level, instantaneous will be this much and instantaneous will be this much, and this will be the creep, this will be the creep. So, instantaneous is this much, this will be the creep. If I consider this stress level, this is the instantaneous, this is the creep level, this is the creep strain. So, at any point of time, any level of stress, this occurs below the failures, below the strength level, and you find there is always creep. So, that is what is creep we have defined, we define creep like this, right. Now, a related aspect is relaxation. To understand relaxation, let us consider this pre-stressed concrete element, an element of concrete, just hypothetical element of concrete, something like this, just an element of concrete, and I have put a pre-stressing bar there. So, I have put a pre-stressing bar, it is stressed, tensioned, pre-tensioned, and then I have just so pre-stressing bar, this is what I have done. So, I have just pre-tensioned it, and this will result in a compression in the concrete, through this bar there will be resultant compression in the concrete. So, concrete will get compressed, and therefore, some elastic deformation would occur. So, it is reached to this level, this is the after the elastic deformation, it would have it would have actually shortened. Now, if I allow this continuously for a long period of time, actually I will find some deformation which I have not shown here, finally, over a long period of time I might end up getting further release of further compression of this whole thing, if I have just kept this material in the long run. So, this will be my creep, this will be simply creep, this will be simply creep, this will be simply creep, but then that is what we have explained earlier. Now, let us look at relaxation then. Okay. So, the creep was something like this. Now, what I do now, take this same after elastic deformation, take this specimen and then provide some restraint to this, provide some restraint to this. Do not allow it to shrink, as I was saying, due to creep it would have gone to this level, but I decided that I will restrain it and will not allow it to go to this level. So, what will happen? Net effect would be, because it is after creep its dimension should have been somewhere here, but I have restrained it. I have restrained it. This restraint means I am effectively applying a tension. I have, this restraint means I am applying a kind of tension, and this tension neutralizes the compression. So, the original compression which I have provided through pre-stressing is actually get reduced, it will get relaxed, and this is called relaxation, this is called relaxation, this is called relaxation, this is called relaxation, this is called relaxation. So, therefore, if I diagrammatically try to look at it, this is my edge, and then at T 0 I have provided sigma 0 like this before, and elastic strain is like this, but now instead of allowing it to deform further or the strain to increase, what I have done? I have restrained it. So, as I restrain it, the stress will get neutralized by the kind of a tension that comes in, because I have restrained it. Its natural position would have been somewhat different. So, it this, as we said, there will be a kind of, since it is restrained, there will be a kind of tension which will actually neutralize this sigma 0 value, and therefore, there is a reduction in the stress, and this is what we call as relaxation. So, relaxation, since the creep varies with time, relaxation will also vary with time, and since creep was it was something of this kind, creep was something of this kind, relaxation will be in the opposite direction. So, here is the stress, not the strain, here is the stress, stress get reduced, and relaxation at any age will be given at sigma 0 minus sigma t. So, this is your sigma t, this is your sigma t, this is your sigma t. So, this is the sigma t. So, sigma 0 minus sigma t. So, you see this, if it is restrained specimen, creep gets actually reduced, and through this pre-stressed concrete element that I tried to show you, actually what I am implying is that this is very important in pre-stressed concrete. We will just discuss about that sometime later on, where creep is important, very important, certain type of structures, or where in the situations where creep is important. So, this is what is relaxation. So, so far we have defined creep, and we have also defined what is called relaxation, what is called relaxation. Now, if I withdraw, what happens if I withdraw the stress? If I withdraw this stress, this was my strain original, and I withdraw the stress, right. So, time since application of the load. So, this is your T, and I withdraw this stress. Now, what I find is the strain, it actually comes down, it comes down, it comes down. So, this is, but then it does not come back to the 0 level. I have applied stress, this is the elastic strain, this is the elastic strain at sigma 0, elastic strain, then this is the creep strain, and then I just withdrawn the load completely. So, it comes back. So, this is actually instantaneous recovery, kind of some of the elastic strain will be recovered, but then it does not come back to the original state, it stops here only. So, this is creep recovery, with time some amount of recovery occurs, this is called creep recovery. So, my residual deformation is here, residual deformation is here. So, there is creep recovery, there is residual deformation still remaining, and which it does not come back to 0. So, there is a residual deformation, and recovery will have two component. One is instantaneous recovery as soon as I remove the load, somewhat like elastic strain. So, instantaneous recovery of the strain, but after that gradual decrease, gradual recovery of the strain will occur, and that we call as creep recovery. Now, you can see that this is in two state. If it is stored dry and it is stored wet, if it is stored dry and if it is stored wet. In wet condition, of course, creep is somewhat less, it is stored wet completely, it is less actually, and then creep recovery is, but the behavior as far as further after unloading. the behavior is almost similar to whether you stored it dry or stored it wet. All right. So, this is creep recoveries, right. So, we have what we have seen so far what is creep relaxation related phenomena and how the creep recovery occurs. All right. So, we can proceed further, and by proceeding further we can look into mechanism of creep. So, we can proceed further and then we can look into mechanism of creep. Now, what is mechanism of creep? Well, actually the problem is except mechanism of creep is still unclear. It is not well understood as yet. There are of course, some kind of theoretical modeling being attempted, but there is a lot of debate on it. There are debates available on it. Okay. So, at the moment exact mechanism of creep of concrete is not clear, or creep in cement paste is not clear, but it is one thing understood that it is related to the gel and gel water, it is related to gel and gel system, capillary, the pore system of the concrete. So, gel pores related to gel pores. Generally, it is related to adsorbed or interlayer water. Generally, it is related to adsorbed or interlayer water. All right. And one thing has been observed that concrete after removal of all evaporable water exhibits little creep, exhibits little creep, exhibits little creep, exhibits little creep. Basically, if you remove all water, but then it might confuse you a little bit, because I said creep in wet situation. If it is fully saturated, completely wet situation, if you keep it, there will be no movement of water actually. But if you have removed all the evaporable water and then then try to study the creep, it shows that the creep is relatively less. So, therefore, it has something to do with those evaporable water or the water its presence. As I said earlier, that it occurs at all stress levels within the service stress range, that means before failure, and it has been observed that it is linearly dependent on the stress when the pore water content is constant. So, if you are not allowing it to dry or anything of that kind, seeing the pore water content is constant, then it is linearly related to the stress level, when pore water content is constant. So, it occurs at all stress level. So, there is something to the pore water level, that is what we are understanding. If you remove water, then you do not get creep really, it does not exhibit creep. So, therefore, it is related to adsorbed or interlayer or water present in the cement hydrate system, that can be understood. When drying occurs, I mean from saturated, see one case is you have dried it and then studying the creep, completely dry. But if you are looking at during the drying process, drying creep occurs when water moves out. Of course, shrinkage also occurs simultaneously. It is very difficult to separate out shrinkage from creep, because many cases both are related to water movement and the gel water gets involved in both the cases. So, it is difficult to actually separate them out, especially when you are studying the drying creep. And internal movement of water to empty pores in sealed specimen causes creep. So, in sealed specimen, movement of water to empty pores causes creep. See, you can understand there are some sort of the statement I am making, it is not, it does not straight away get into the mechanism straightforward. There are more complexities involved and the understanding is not yet clear. Certain observations are, one can list a huge number of observations that has been seen in laboratory, but generally it is attributed to movement of water and the adsorbed water and so on and so forth. Basically, it is the calcium silicate hydrate CHS of hardened Portland cement, and that's that's where it originates. That's where that's where it originates. In case of dried or when you have removed the water, that's what has been said, that creep is caused by slip due to bond rupture along the bond, along with bond restoration at the adjacent site when water is removed. So, when you remove the water, CHS has got van der Waals kind of bond, and this rupture of these bonds rupture of these bonds causing actually some sort of further deformation, and then of course, the bonds restores elsewhere, bonds gets restored elsewhere. So, movement of water from one place to the other actually causes from gel to some other place, from some gel to some other place, causes rupture of some of the bond which are associated with the water, actually the van der Waals kind of bond that we talked of in case of CHS gel. You know, it is across those interlayer water, that is what we mentioned in the beginning. When you remove the water, there comes some kind of slippages can occur due to bond rupture, but then water moves into somewhere else and there the bond actually restores. So, these are some kind of ideas that has been put forward, but one has to remember the cement paste or concrete, you know, I am talking of cement based concrete, hydration process is continuous, it does not occur instantaneously and it goes on occurring. So, this is what is actually you can say aging, you know, the material changes with time, and in any case you have large specific surface of the gel, and these ones have some roles to play in creep, these ones have some roles to play in creep. So, continuous hydration process, the change that occurs, the aging of concrete, and of course, large specific surface associated with the gel, the water getting absorbed there, and this have all some role to play in creep. So, concrete undergoes actually gradual changes in response to stress and environment, because hydration is also occurring, and if you have put in some stress, there is an interaction with the stress and the changes that is occurring, and it will also depend upon the environment, relative humidity and so on and so forth. Thus, it is actually extremely complex thermomechanical behavior, and you know, this exhibits extremely complex thermomechanical behavior, and creep is no exception. So, that is why it is so difficult to actually predict, but one thing we have understood from our discussion so far, that is related to the gel water and its movement, gel water and its movement, right, may be related to porosity and so on and so forth. So, as we see, we will see the factors affecting, we will have some idea, but exact mechanisms are still not very clear. So, now we can look into factors influencing creep. Let us see what are the factors that influence the creep. First of all, modulus of elasticity of aggregate, we will see more of it, but we can understand, you know, because the deformation of the concrete, if you are looking at it would be affected by modulus of elasticity of the overall material, and in the overall material aggregate modulus of elasticity plays a role. Therefore, modulus of elasticity of aggregate is an important one. Water cement ratio essentially governs the porosity and pore structure of cement based material, and therefore, water cement ratio will also, you know, is a factor that influences the creep. Curing condition, the environmental condition, whether it is fully saturated or what it is, the water movement is, you know, finally it is water movement, therefore, curing condition, and also it is a complex interaction of hydration process which continues over a long period of time. So, therefore, curing condition becomes important. Relative humidity, environmental condition we just mentioned before, and volume to surface area ratio is important, because depending upon volume to surface area ratio, evaporation rate, you know, the movement of water outside the specimen or outside the element would be governed by volume to surface area ratio. The slump is the flow of the concrete characteristics, and fine to total aggregate, and air content, all these are the factors. So, these are the factors we will see how do they affect, and how one can, then we will look into how one can use this for predicting creep, All right. So, these are the factors. Let us see individually some one of them, how do they affect. Aggregate modulus of elasticity, this is an important part, and you find that as the modulus of elasticity of aggregate increases, the creep reduces, the creep actually, you know, relative creep reduces. So, higher modulus of elasticity, these are all in GPa, let us say something like 100 GPa or 60 GPa, you know, 60 GPa or 100 GPa. So, 60 GPa, 40 GPa, and relative modulus. So, very little is high, spaced sort of, I mean very little. So, as the modulus of elasticity increases, creep will decrease. So, this is somewhere is a red sandstone, this is a green sandstone somewhere there, marble, river gravel, granite and crushed quartz, basalt and so on and so forth. So, as you increase, as the modulus of elasticity increases, creep reduces. So, higher modulus restrains creep. We can understand this very easily. Actually, creep means more deformation, but deformation, but if it is a higher modulus, stiffness of the aggregate is more, it is not going to deform. So, it will not allow creep to occur, it will restrain the creep somewhat, because the deformation would be restrained by higher modulus aggregate. Higher aggregate content of course, will also result in lesser creep. It is related, because aggregate does not creep, it is the cement paste which shows exhibit, which is responsible for creep of concrete. Therefore, more the aggregate content, lesser will be the creep. This we can see in this diagram. More the aggregate content, lesser will be the creep. You see volumetric content of the aggregate percent. So, this is 100% here, 0% here. So, it increases along this direction and creep in micro strain sort of. So, this some of them are for dry specimen, the rounded one, and these are for wet specimen, and this is creep from the age 1 day, and you can see as you have lesser aggregate, more creep, more aggregate, less creep. So, if you have more aggregate, less creep, and this is understandable, because aggregate do not creep. So, it will not contribute to creep, while paste will do, and although it is not really related to modulus of elasticity, but it is related to the aggregate content. Okay. Finally, affecting the stiffness of the system, because more aggregate means more stiff, the system, I mean more will be governed, stiffness will be governed by the aggregate modulus. The next factor is water cement ratio and age of loading. If you look at water cement ratio and relative creep, somewhere around 0.65 I am saying creep is, let us say 1, or dividing all creep by that is at around 0.65 or so, then what we find is that higher water cement ratio more creep, lower water cement ratio less creep. Higher water cement ratio more creep, lower water cement ratio less creep. I mean this is related to porosity, right, this is largely related to porosity. So, what it says, if I have age of loading increases, creep should decrease. So, age of application of the load, if it is 7 days, if this is 1, then at 100 days this will be something like 60% of that. So, relative creep is on this axis, and therefore, we can understand more water cement ratio means more pores. So, if scope for water to move from water filled pores, all pores are unlikely to be saturated, even if you have some water content, unless it is fully saturated, that is a separate situation. Maybe we did not see for the wet specimen, the creep will be very less. That is what we have seen in the earlier, when we said dried specimen and wet specimen, it is not fully dried, evaporable water was there, but at the same time wet specimen fully, it is fully saturated situation, the movement of the water will be relatively less. And if it is fully dried, there will be some creep, but creep is much less, because because of it can continue because of slips that we talked about between gel water, gel particle, viscoelastic behavior of the gel system, that may still cause some, but it is relatively less. Anyway, coming back to here, that higher water cement ratio means more pores, and it is unlikely to be fully saturated. So, some pores will be empty, some will be filled in. More, that phenomena is likely to be more here. So, water can move from filled spaces to unfilled spaces, while in low water cement ratio, lesser the overall pores, and the this kind of movements will be restricted. Besides, through gel pore it has to move only because capillary segmentation and all would occur. So, movements also would be relatively difficult. Now, this same thing follows as hydration progresses. Obviously, the gel structure or segmentation occurs and gel structure become very solid. So, if you apply load later, you are likely to find less creep. If you apply load later, you are finally likely to find, you are applying load now in a system which is more matured. So, therefore, you are likely to find less creep, relative creep as shown here, as shown here, as shown here. What about relative humidity? Well, it is the percentage relative humidity 50%, 70%, 100%. So, you see if you have 50% the creep is more, 100% it is relatively less, creep absolute values in micro strain, and you can see that it is 50% it is more, and this is basically time t since loading 5 years 28 days. So, time since loading. So, after loading 28 days after loading, 10 days after loading and so on and so forth. So, if you after loading you find the 10 years. Now, relative humidity, higher the relative humidity, less. Again same movement of water, relative humidity means gel should be more or less saturated. So, movement of water from gel pores to other gel pores, that will be relatively less, right, and in saturated in case of 100% relative humidity. So, gel pores will be all saturated. So, therefore, adsorbed water movement will be relatively less, adsorbed water movement will be relatively less. Capillary pores hold absorbed water, suction, capillary suction. The gel pores hold adsorbed water, vapor also can come and get adsorbed at the surface, because it has got enormous surface area. That is what we said, that it has got very high specific surface, earlier we mentioned that. So, therefore, relative humidity, higher relative humidity, lesser will be the creep. Volume to surface area ratio. Now, if I look at volume to surface area ratio, so ratio of 30-year creep to this side is 30-year creep to elastic strain, 30-year creep strain to elastic strain, and volume to surface area ratio. So, what you are looking at is epsilon 30 years on the y axis, epsilon 30 years by 30 years by epsilon 0 elastic strain. So, this ratio, so the creep would be more if this is of course drying concrete, this side is sealed concrete. So, if you see, so basically this is an infinite creep, creep at infinity divided by this. So, 365 days at the edge. Now, volume to surface area ratio more, less is the creep. Volume to surface area ratio greater, higher V to surface area ratio means less creep. Why? Why so? Well, it is through this surface, through the surface evaporation occurs. So, higher volume, or if I say S by V, more S by V, more surface area per unit volume means more evaporation possible, drying is possible. So, moisture movement is possible. So, in other words, less V by S is more creep. So, high V S by V more creep. So, low V by S higher creep, higher. So, that is what it is. So, you see that lower values you get high, lower V by S you get higher creep, lower V by S one gets higher creep, lower V by S you get higher creep, and this reduces. So, because of the evaporation losses, the water movement gets restricted, etc., and therefore, so loss of water reduces is V by S ratio, hence lower creep. Loss of water reduces with V by S ratio, hence lower creep. So, this is the explanation for this one, V by S. Now, what about temperature? Temperature also affects the creep. Supposing I have 60 degrees centigrade cured at the test temperature, this is a relative creep. So, higher the temperature, there is some sort of a peak, and beyond that there is a reduction. But if you cure at 21 degree centigrade and heat to the test temperature, that is 40 degree centigrade, 1 week before loading and then do the loading, you find that creep actually increases with the temperature. So, what you are doing? You have actually cured at 21 degree centigrade, right, and heated to test temperature. So, what you do? Then you heat it to 40 degree centigrade or 60 degree centigrade and keep that sustained loading under that same condition. So, now what happens is there is an increase in the creep. So, you have 21 degree centigrade cured and this situation, but here cured and tested at this temperature. So, you do curing at 40 or 60 degrees centigrade. Now, the problem is when you are doing, let us say, curing at 80 degree centigrade, the curing will not be, the pore structure will not be uniform, pore structure will not be uniform, pore structure will not be uniform, right. And beyond that, when you are curing at 100 degree centigrade, practically evaporable water has all gone. So, most of the evaporable water will vanish actually. So, this will not help. Beyond that, of course, you have non-uniform structure. At the same time, the most of the evaporable water will vanish as you go close to 100, most of good lot, and therefore, creep tends to reduce. So, that is what we are saying when you are actually removing some of the evaporable water and during curing, because you are curing at 90 degrees, say here you are curing at 90 degrees centigrade and then applying the load. So, curing at 90 degrees centigrade and then applying the load. So, this at this point the water has evaporated, and therefore, but up to this point still there is an increase in the creep, but this creep is less than this, because the some water has moved out, some water has moved out, right, some water has moved out. So, creep increases with temperature, that of course, we have seen, but then it has something to do with the movement of water, and that is what explains the situation, right. For example, this is again temperature, concrete previously dried up to 105 degrees centigrade, sealed specimen, and this is unsealed concrete. So, you have dried, it goes to a very low level, previously dried to 105 degrees centigrade, right, and the relative creep is less. So, dried concrete relatively, but if you have dried to 500 degrees centigrade or so, 300 degrees centigrade, unsealed concrete, then obviously, creep seems to be more, and this is also the case, So, relative creep tends to increase at 0 to 75 degrees centigrade and higher. So, higher temperature, it is related to, since it is related to moisture movement, this is what is happening. Sealed concrete at low temperature shows low temperature, at low temperature, sealed concrete at lower temperature, and dried concrete obviously creep more. So, this is at sealed concrete at lower temperature, this one. So, this is what it shows the behavior minus 25, 0, 25 and so on. So, if it is sealed, the moisture is still retained, So, if you increase the temperature, actually it will have a tendency to show high creep. So, with all these factors, one can think in terms of predicting the creeps. Roughly 25% of 20 years creep occurs in 2 weeks. So, it is, as we have seen creep behavior, we have seen that it is elastic strain, and then from this it follows like this. So, initial rate is pretty high. So, 25% of 20 years creep occurs in 2 weeks, 50% occurs in 3 months, and 75% in 1 year. So, most of the creep seems to occur within the first 1 year, 75% of 20 years. So, it is asymptotic behavior later on. Therefore, creep with time, gradually creep with time, creep will actually reduce down. Now, there are guidelines through which we can actually estimate creep. Approximate expression will be given like this: creep at any time t after 28 days, let us say, let me call it as CT, and the approximate expression is that if I know C 28, Then for sealed and saturated concrete it will be 0.5 T to the power 0.2. For drying concrete this will be given as minus 6.19 plus 2.15 ln T to the power 1 by 2.64. So, this is some empirical equation. As T increases, because its T increases, creep reduces. Creep, time for drying concrete, the relationship is like this. So, as T increases, creep reduces. T increases, creep reduces, or rate of creep actually reduces. That is what it shows. Rate of creep actually reduces. So, as T increases, rate of creep reduces. It is asymptotic curve, and that is why it is like this. So, as T increases, this is 0.2, this is 0.2, T to the power 0.2. So, if you differentiate this, you will get 0.2 T to the power 0.2 minus 1, and you can see that as T tends to infinity, it will tend to go to a constant value, it will tend to go to a constant value. So, whatever it is, basically they would like to, this would like to, one is asymptotic. So, the formulas are fitted in this manner. But better way would be to predict through some of the guideline, using some guideline like ACI 209R method. So, this is method appropriate to normal weight concrete under constant environmental conditions. So, approximately one can actually predict, but remember these are for design purpose or estimation purposes for practical uses. So, they would like to it should be for practical purposes. Actual environment may not be as constant as thought, but still this could be applied. This could be, one can use this for estimation. So, let us define something called specific creep. Let us define something called specific creep. Specific creep at time C t t 0, where t is the time at which I am trying to find out the specific creep. T 0 is the time of application of the load, is the creep due to unit stress applied at T 0. So, if you apply sigma equals to 1, then the creep that you get C at time t, and T 0 is the time when you applied, that I call a specific creep. So, specific creep at any time is the creep at that time due to unit load, due to unit stress, or sorry, not unit load, unit stress applied at T 0, right, due to unit stress applied at T 0. Then another terminology, creep coefficient, which is denoted by phi, is the ratio of specific creep to initial elastic strain. So, phi T T 0 is nothing but C T T 0 divided by epsilon 0. So, this is basically related to elastic strain, right. So, creep coefficient is the ratio of specific creep. So, this is for unit load, and this is the initial elastic strain. So, elastic strain, if you want to find out the creep, specific load multiplied by epsilon 0 will give you the specific creep. So, creep coefficient multiplied by elastic strain will give me specific creep, right. It will give me specific creep, it will give me specific creep. Ultimate creep coefficient is the long term creep coefficient, and we can be related to creep coefficient at any time. So, creep coefficient we have defined as creep coefficient we have defined phi t t 0 we have defined as C t t 0 divided by epsilon 0, right. But ultimate creep coefficient, that is the long term, this is the long term. So, long term this ratio of creep coefficient can be related to creep coefficient at any time. So, this can be phi infinity T 0 is the time of application load, can be related to this. That is what we are saying, all right. In other words, phi t t 0 at any time is t t 0 to the power 0.6. So, this is a relationship between this and this. So, this is related by an empirical formula, and that is the ACI guideline. it is actually t minus t 0, t 0 is the time of application of the load, t is the time at which you are finding out the creep coefficient, and t minus t 0 to the power 0.6, 10 t minus t to the 0.6, t minus t to 0 to the power 0.6 into phi infinity if you have applied the load at t 0, if you have applied the load at t 0, right. Okay. So, it is if you have applied the load at t 0. Ultimate creep coefficient is further related to various factors. So, this I can relate to various factor. If I can relate this to various factor, I can find out this, I can find out this and multiply this by epsilon 0 into phi t t 0, that gives me c t t 0. So, creep at any time I can find out. First of all, I must find out this will be known to me, first find out this, and to find out this can be found out, and this is related to various factors. These are related to various factors. Okay. This is related to various factors. So, let us see how they are related. Phi t 0 is given by 2.35 k 1, k 2, k 3, k 4, k 5, k 6, some factors, 6 factors, some 6 factors, simply phi this is k 1, k 2, k 3, k 4, k 5, k 6. So, there are 6 factors to which you can relate. Now, remember these factors are what we have seen earlier, like aggregate modulus, aggregate content, then water cement ratio, volume to surface area ratio, and so on and so forth. So, this we can estimate in this manner. All right. This is this of course, is no complexity of mathematics involved here, but one may not be able to remember this, but using a procedure simply, because these are all empirical equations. These are all empirical equations. K 1 is given as 1.25 T 0 to the power minus 118 for moist curing and age of loading greater than 7 days. So, these guidelines are given, or it is equals to 1.13 T 0 to the power 0.095 for steam curing and age of loading 1 to 3 days. This is a more practical situation. See, age of loading would be most of the time more than 7 days. It rarely would be less than 7 days, right, because deshuttering etc., etc. After that, even construction load, most of them will come. But if you are doing steam curing, then load can come fairly early, because steam curing is done to attain high earlier strength. So, that load can be applied easily. So, this is again a kind of empirical or guideline available. So, K 1 was, what was the K 1? It is for moist curing and the type of curing. K 1 is a factor related to curing condition. K 1 is a factor related to curing condition. So, K 1 curing condition. K 2 is related to relative humidity. K 2 is related to relative humidity. Okay. K 2 is related to relative humidity, and there is more about it, but I think I have picked up only one portion, because if one is interested in calculating for various condition, various relative humidity situation, one may go back to ACI the document that I mentioned just now, ACI guideline 209 R, but a part of it I am just mentioning here. For example, I am mentioning here related to relative humidity. If it is more than 40%, the equation is given like this, where H stands for relative humidity in percentage. So, H stands for relative humidity in percentage. K 3 depends on the member volume to surface area ratio. We have seen that this is a factor, and you have a table, part of the table is reproduced here. Part of the table, it is not really full table. Volume to surface area ratio 12.5, it is 1.3, 25 it is 1.1, 37.5 it is 100. Now, we have seen that more surface area means more creep likely to be. So, lesser this value is, this lesser this value, more surface area means lesser this value. So, lesser this value, creep will be more, lesser this value, creep will be more, and this is, so this V by S all in millimeter, V in millimeter, surface area also in millimeter. So, volume to surface area ratio will be in millimeter. A part of the table actually I have just reproduced, table is much wider. So, one can use this, and we have understood why this actually, why this occurs, because the drying or moisture movement can be easier when you have more surface area, and therefore, when you have more surface area, this value is less, this factor is higher. Remember that we said it is 2.35 K 1, K 2, K 3 etcetera, K 6. So, phi infinity at T 0, this is given as ultimate creep coefficient is a function of K 1, K 2, K 3. So, higher the values of K 1, K 2, K 3, more will be the ultimate creep coefficient, in other words, more will be the creep. Then we have K 3, which we said that was related to V by S, and V by S, K 3 is K 3, K 2 was related to relative humidity, K 3 was related to this. So, values of K 3s were given, and some cases it is related to the period of creep also, given by this kind of a formula. For up to 37.5, this table was good enough, up to 37.5 this table was good enough, and 12.5 to 37.5. For other values, this formula is also given. T is more than 1 year, T is less than 1 year, two formula is given, and V by S greater than 95. So, greater than 37, 37.5, 95 mm, those values are, these values are given. Now, K 4 is related to slump of the concrete. K 4 is related to slump of the concrete, in other words, compaction and flowability of concrete or compaction of concrete. So, or possibly related to water content. So, higher water content is higher slump, S is slump, and K 4 is related to slump of the concrete, which is in terms of higher water content. Then K 4 was related to slump, K 3. So, what we have seen, just repeat it K 1 relates to the very first factor relates to curing condition. The second factor relates to relative humidity. Third factor relates to volume to surface area ratio. Fourth factor relates to slump of the concrete, and the fifth one relates to the aggregate content. So, AF is the fine aggregate content and A is the total aggregate. So, relatively this ratio is more of the coarse aggregate content, less will be the creep, that is what we have seen. So, because it will actually restrain, and therefore, K 5 is related to the proportion of coarse aggregate in the system. K 6 is related to air content, K 6 is related to air content, higher air content, high will be possibility of more water movement. So, therefore, A is the air content. So, higher the air content, K 6 is higher. So, what we see is that it all depends upon all these factors, and then we define a term. So, what we have seen, K 1 curing condition, environmental condition I can say, K 2 relative humidity, again environmental condition, K 3 volume to surface area ratio, K 4 slump, K 5 fine to coarse aggregate ratio, and K 6 is air content. So, these are the factors to which is related to. Then phi, what we have got is phi, we got actually phi, that is ultimate creep coefficient, which I can multiply by a multiplying factor, which is a function of t minus t 0, and I can get is the creep coefficient at any time. And if I know the creep coefficient at any time, I can find out actually creep at any time multiplying by elastic strain for unit stress. Creep function phi is elastic strain plus creep deformation. So, creep function is elastic strain plus creep deformation. So, under unit stress. So, under unit stress 1 divided by this is epsilon 0 under unit stress, and this is creep. Now, this also can be related to unit stress, because we said phi t 0 was nothing but epsilon 0 epsilon 0 multiplied by C is equals to C T T 0. So, therefore, this can be this is epsilon 0 is nothing but this is nothing but 1 divided by E. So, this can also be, let me just rewrite this, let me just rewrite this separately, let me just rewrite this separately, let me just rewrite this separately. What we said was Cripps function is phi and it is given as 1 by this is C plus. So, this I can write as 1 for unit stress, all is elastic strain plus Cleese for unit strain. So, epsilon T 0 unit. So, this is the elastic strain plus this can be written as phi T T 0 multiplied by 1 divided by E 0. So, therefore, you see that this is 1. What is this? This is basically C can be written as epsilon 0 multiplied by phi T by T 0 and epsilon 0 is what 1 over E 0. So, I can just replace it like this. So, therefore, I can write this whole thing, the Cripps function as 1 by E t 0 1 plus phi plus this E t 0 can be taken common, modulus of elasticity at that time, and this is what it is 1 plus Cripps. So, this is for unit stress, Cripps function is for unit stress, and that is how I can estimate. So, E is related to cylinder strength. This E can be related to cylinder strength, because we know it is 5000, I mean cube strength was 5000 under root f c k. So, E is related to cylinder strength by SEI formula, and one can obtain this. So, that is how we can predict the Cripps function, which is for unit stress, right, at any time t. So, that is prediction of Cripps. We will have more of the prediction of Cripps in the next class. In this class, therefore, what we have understood is, this lecture we have understood is creep and relaxation. We have looked into mechanisms and we have looked into factors affecting Cripps and some part of the prediction. The rest of the prediction, some more of the prediction we will look into in the next class, and then we will look into measurements and so on. Now, as far as prediction is concerned, just I would like to mention one more thing. At the moment, we have come up to Cripps function, through which I can predict this Cripps for unit stress. So, with this we conclude our this lecture. Thank you very much.